Hello everyone, I'm Jifan. The project our group studies is algorithm to solve real travel planning problems. In this presentation, we will show the solutions to 4 travel planning problems in our project. The first one is the path is system problem, which is to decide whether there exists a path between 2 spots. The problem is modeled into a graph with vertices of spots. If we can access another vertex from a vertex, there exists an edge between them. The weight of the edge can be the traveling time, the distance, the money, and the gasoline cost or the electricity. The edges are undirected, and their weights can be positive or negative. This problem can be solved by BFS or DFS. Their pseudocode are shown on the slides, and both of them takes OV plus E to run.
Hi, my name is Jing. Problem 2, consider the situation that you plan a trip around your home and wants to travel with minimum cost. This is a typical single source shortest path problem. In real world, the edge representations may vary. For example, as the fact that the electric car consumes electricity up hills while it recovers energy down hills. Edge denotes electricity may become negative on one of the directions. And next page, please. To solve this problem, we know these two algorithms, and here gives a comparison. A positive weighted directed or undirected graph, the Dijkstra's algorithm performs better than Bell-Manifold as it has a lower time complexity. However, when negative weights exist, use Bell-Manifold to handle this situation. And next, my teammate Zhou will present.
Hi, I'm Zhou, and I'll introduce the problem 3. Suppose such a situation during the traveling. Before traveling, we want a map recording the shortest path between each pairs of spots. With such a map, after I visit spot X and I plan to visit spot Y, I can easily get the shortest path from X to Y without recalculation. So this question can be modeled as the all pairs shortest path problem in a graph and can be solved by the Floyd-Marshall algorithm. The basic idea of Floyd-Marshall algorithm is dynamic programming, as it notes that the path value between two cities I and J may be reduced by passing another city K. The implementation is easy as shown on slides, and the time complexity is n-cubed. Fourth problem is the traveling salesman problem. For TSP problem, we will introduce both precise and solution and approximate solution. First is the precise solution. Those traveling sales problem is an NP-complete problem. We can still employ non-polynomial algorithms to obtain a precise answer for small data inputs. The brute force method is easy to permute all possible paths, but with n factorial time complexity. With the study of dynamic programming in shortest path problem, we were inspired to solve TSP by dynamic programming. The basic intuition is that if we found the shortest path from 0, 1, 2, 3 to n and back to 0, the path from 1, 2, 3 to n and back to 0 is also a shortest path. So we can solve the question by some subproblem. The first thing is to define the DP matrix. We use DPIV, where I is a vertex and V is a set of vertices to record the shortest path value that start from I, visiting all vertices in V for one and only one time, and back to vertex 0. With such definition, we can find state transition equation for this problem. When V is an empty set, DPIV represents from vertex I to vertex 0 directly, which is given in the input graph. And this is the base case for our solution. When V is not empty, we will loop every vertex K in V, calculate the distance from I to K, plus the shortest path value from vertex K to vertex 0, passing all vertices in set V minus K. And the minimum one is the value of DPIV. Another skill in this solution is using bit mask to represent V in the DP matrix. Here is an example with 5 cities, 0, 1, 2, 3, 4, and this slide shows the DP matrix. And here shows the process of subproblems. What we want is D0, 1, 2, 3, 4, which can be solved by the 4 subproblems. And finally, the subproblem is just the base case, and we can use a bottom-up method to fill in the DP matrix starting from the base case and get the final answer. Let me show the code and the result. Here, my input has a data size of size 9 cities. It found the shortest path with the value 28, and the minimum path is from 0, 1, 2, 4, 5, 8, 7, 6, 3, and back to 0. And can be executed in a very small time, but it cannot work on our bigger data set with 34 cities because of the high complexity.
And let me introduce another solution to the TSP problem. Although the dynamic programming can obtain the optimal solution, its time complexity is relatively large. However, in daily life, rather than pursuing the optimal solution, we may need to obtain an approximate solution in a relatively short time, especially when the amount of data is large. And greedy algorithms can do this. The algorithm is called nearest neighbor heuristic, which is very straightforward. Visit the nearest unvisited spot each time until all the spots have been visited. The implementation is also very simple. First, we will build a graph of the spots. The graph is represented by an adjacent matrix, which stores the distance between the spots. And here is the implementation in Python. It takes the graph and the source as the input and will give the path of the TSP tool and the total cost of the tool as the result. The advantage of this algorithm is obvious. According to the code, the time complexity is n squared for the input graph with n vertices. And this time complexity is relatively small and can give the result very fast, even with a large input. However, it is difficult to prove that the approximate solutions are good enough. In fact, the nearest neighbor heuristic does not have a constant approximate ratio for the traveling salesman problem. It is proved that the approximation ratio of this algorithm is theta log n, and since it is a logarithm function to n, as the number of vertices grows, the difference between the approximate solution and the optimal solution also grows. So when the size of input is large, we may end up with a less satisfactory result. And here I will give 2 examples for this algorithm. And this is an example of 15 spots. It can give the optimal solution since it is not very large. And for this example with 48 spots, it only gives an approximate solution. And I can run this. I can show you how to run this. And we can see this is the graph we obtained. And this is the path it gives, and it costs this amount of distance. And I'm satisfied with this since the approximate ratio for this instance is only about 1.2, and both of the 2 examples are calculated very fast, and it is better than the dynamic programming.
Hi, I will introduce another solution to the metric TSP problem. The metric means the graph follows the triangle inequality. The algorithm is called the Christoffel algorithm. It has the approximation ratio of 1.5, and it takes cubic time complexity faster than the DP solution. The main idea is to combine MST and minimum weight perfect matching. And the algorithm is like this. Then I will show an example step by step. The example is this is a complete graph with 5 vertices and 10 edges. The DUV denotes the non-negative distance between U and V, and the DA denotes the sum distance among edges subset A. And our goal is to find the Hamiltonian cycle with the minimum total distance. First, we create an MST. From the lecture, we know that the DT is smaller than the optimal tour. We use Prime's algorithm to realize this and test both binary heap and Fibonacci heap in the implementation. Both time complexity is lower than cubic. And second, we find vertices with odd degree. Here, that is B, C, D, E have the degree of 1. By handshaking lemma, the cardinality of this set is always even, and this step takes linear time. And third, we create the complete subgraph in quadratic time based on the odd degree vertices set. Because the number of nodes in O is even, a perfect matching always exists in this subgraph. So next, we create a minimum weight perfect matching in this induced subgraph. Here, that is B, C, and D, E. And let an asterisk denote the optimal tour on subgraph, and it is smaller than the optimal tour on the whole graph. And we can derive that DP, the minimum weight perfect matching, is more than the half of the optimal tour edge asterisk. And this takes cubic time with Blossom algorithm. And the fifth, we find the multigraph and by adding minimum weight perfect matching to MST. Combining two inequalities, we have the multigraph, which is smaller than 1.5 times the optimal tour, and this takes linear time. And the sixth, we generate the Eulerian tour. Here the cycle is A, B, C, A, D, E, A, and this tour visits every edge exactly once, because no changes on edge, so this E is also smaller than 1.5, the optimal tour. And last, we finally get the Hamiltonian circuits from Eulerian tour. And this circuit deletes repeated vertices except the stop vertex. That is, we delete AD and AC in the Eulerian tour, and we add CD. And because it follows the triangle inequality, so the Hamiltonian circuit is smaller than the Eulerian circuit, and is smaller than 1.5 the optimal tour. And this step takes a linear time. And so the approximation ratio of this Christoffel algorithm is 1.5, and finding the minimum weight perfect matching takes cubic time, which is outer bound in the whole procedure. So Christoffel algorithm has cubic time complexity. And then I will show my program. Here we run a data small with 9 points, and we can see that the Hamilton circuit is from point 1 to point 1, and the total cost is 32, which is within the 1.5 times the optimal tour, which is 28. And let's run a bigger data size with 34 points, and we can see that it gives a Hamiltonian circuit, and its total cost is 170. And that is all about our presentation. Thanks for watching our video.